for attending today. We appreciate the great attendance. This is awesome. Let's talk about Monte Carlo assimilation and the bootstrap. So really all about uncertainty. Avi's already given some details about datum and who we are. I'm not going to go through that. I should mention one thing, and that is that while I teach data analytics, geostatistics, and machine learning, I do partner with another co-founder in this, Dr. Foster, who does an excellent job at data science, covers all the high performance computing, how to scrape things from different sources, a lot of feature engineering and so forth, and all the way to building out really cool dashboards and automating common tasks for engineers and geoscientists. So he does a great job. He does a lot of, check out his webinars, check out his training too. Okay, what are we gonna do? So what we'll do is I'll do a really quick introduction. Anyone who's been to these webinars before, I apologize, but just a little bit about myself so you know who I am. Now, James, I see a hand up. Go ahead and send something in the chat window if you do have a question or comment. And if you're having any issue with observing or anything, just check in with Avi. He can help you with connectivity issues or any technical problems. All right, and Happy New Year. Hey, Happy New Year. Thank you very much for that message, Mohammed. Indeed, we're happy to talk about this. Okay, so let's go ahead and give a bit of an introduction. To those of you who have never met me in person or heard from me before, my last name is a bit of a clump of consonants, but you can pronounce it Pyrcz. If you do it like that, you're doing it as well as my family who came from Canada, 100 years in Canada, and before that, the Ukraine, Poland, and so forth. So it's Pyrcz. And if you say it like that, that's fine. I'll respond. I'm from industry. I started as a professor just back in 2017. I do a lot in industry. I have a lot of practical experience. Everything I teach, I've done. And I think that's important. That was part of the reason I didn't go straight to being a professor. I thought this was really cool to get some industry experience. I had too much fun in industry. It turned out to be 13 years. And I have to admit, I very much loved it there. I do enjoy being back working with industry. So I'm very flexible. If you have ideas as we move along here, if there's something you want us to spend more time on, send it in the chat window. We can discuss. I like to be more learning focused rather than schedule focused. So let's go ahead and have the discussions that are important. Jump in at any moment. I'm available. People often fire me emails, ask questions. Even people drop by my office back when we were all in person or drop me a line, and I'll tell you what, I am responsive. I'm an engineer and a geoscientist. If you're a geoscientist and you're not getting my geostat speak, my engineering approach, I can switch and translate and communicate it from the geosciences and the geoscience workflows. I've worked on both sides. I have a lot of my background and my education is both engineering and geoscience. And I'm just starting to brag. I just really want to say that I do a lot of teaching in industry. I think Avi, it was like 20 companies or something last year. I always lose track. There was many companies represented in my courses and so forth. We do a lot of teaching in industry, and I do support professional development everywhere. People check out my Twitter account. Anybody here on Twitter? Anybody see my stuff on Twitter by show of hands? Mohammed, Baruz, I see that. I see a bunch of you. Very cool, very cool. Hey, awesome, guys. You know, I share resources daily, positivity, ideas, concepts, all in data analytics, geostats, and machine learning. And that's my goal, is to share and make education accessible through Twitter, GitHub, and even my lectures on YouTube. So check it out. I'm really happy to support. Okay, what's the goal today? That's enough. The goal today is uncertainty is ubiquitous. It's everywhere we look. There is uncertainty. And so I want to talk about, discuss, and demonstrate some basic fundamental tools to build out uncertainty workflows. The term we use is uncertainty management. That's what it's all about. We need to work with and manage our uncertainties and be able to get to the decision. Take these uncertainties all the way to the decision so we can make the best decisions in the presence of uncertainty. That's our goal. That's our mission. Let's start out with Monte Carlo simulation. That will provide the prerequisites and the overall workflow, the framework. by which we can then talk about Bootstrap, a valuable tool, an element of that. Okay, so Monte Carlo assimilation. This is what I love about a lot of fundamental statistics. It is very intuitive. It is very straightforward. Monte Carlo assimilation, the basic definition is random sampling from a distribution. That's it. In fact, kind of to take it, to explain it in extreme detail, what we do is we first model the distribution. Now, if you're going back to fundamental statistics, I mean literally build a cumulative distribution function. That's model the distribution. Now, we could talk about that. That could be non-parametric. And what I've done is I've taken the data, sorted it, debiased it, and built and fit a reasonable distribution. Or it could be something more theoretical where we have a known distribution we've inferred, a parametric distribution. It doesn't matter. One way or the other, we have built a cumulative distribution function. That's step one. And that's important. We got to make sure it's representative and so forth. Once we've done that, then we'll draw a random value from a uniform 0 through 1 distribution, 0 to 1 distribution uniform. The fact that it's uniformly distributed means that it actually is what we would call a random p-value or cumulative probability value that we can apply to the distribution without causing a bias. On my exams, I like to ask my students, what's the distribution of p-values? And you would be surprised how many students struggle with this on some of the tests or midterms. What exactly is this distribution? It should be uniform. If it's anything else, you will not get back the original distribution if you sample with those values. It must be uniform. And the way to think about it is the probability of getting a value between 0 and 0.2 should be the same as the probability of getting a value between 0.6 and 0.8. And if you think that through, it becomes a uniform distribution. Then we'll apply the inverse of the CDF to calculate the associated realization. I'm going to define that term on the next slide. The calculation looks like this. It's the inverse of the f of xx. So in other words, what I'm doing is taking the cumulative probability, applying it here, a specific cumulative probability value, a realization of that. We're going to apply it to the inverse of the CDF, the f of x inverse, and we'll get a realization from the distribution. So in other words, I take a random p-value, anywhere uniformly distributed along these cumulative probability values. I go the reverse direction on the CDF, and I get a specific realization from the distribution. Then what I'll do is I'll repeat until I have enough values to complete my analysis. And I'll talk a little bit about that. We'll demonstrate what happens when you use too few values. The method is very powerful. You can simulate distributions that we could not simulate with an analytical approach. We would not be able to get back to it with an analytical approach. So that's a power in it. Now let's define a couple of terms here. First of all, let's recall the random variable. The random variable, the RV, it is defined as simply this. It's a very practical definition. We do not know the value at a location or time for a feature of interest. It can take on a range of possible values, and we'll describe it with a distribution. So it could be a PDF or a CDF, either or is fine, of course. It's represented as an uppercase variable. So the random variable would be X capital, while a possible outcome or data measure would be represented by lowercase x, just lowercase x right there. Now, if you go back here, the random variable is going to be this distribution, and the realization represented by lowercase would be the specific value we drew from the distribution. In the spatial context, we add one further descriptor, and that is location, locality. Because we know in geoscience and engineering, everything's not the same. Everywhere, the random variable is going to change from location to location. Trends, I get to use this word, it makes me happy. Heteroskedasticity, the variance and variability can change locally. So in spatial context, it's common to use a location vector U with some type of index on it like alpha to indicate a specific location of the random variable and of a specific random value realization drawn from that random variable. Okay, so the realization, just to kind of further refine this, is an outcome from a random variable. So if we have the random variable represented from this distribution, we do Monte Carlo assimilation, we get a realization, and that realization would be a specific value we've drawn at random from the distribution, like we showed before. Now, we'll usually denote L equals and an index on the realizations because you never work with one realization. You're going to work with many realizations, big L realizations, and we'll talk more about that shortly. We're going to go ahead and simulate those realizations through the Monte Carlo simulation approach. Now, we also have the location vector like we talked about before because things will change locally. And in general, the geostatistical approach is to expand this into sequential Gaussian simulation and other methodologies where we're doing a joint sampling from many random variables to get what we call a realization from a random function. Now, we're not going to go into those details today. I just wanted to make that linkage. Another point that the geostatisticians talk about quite a bit is the fact that each of the realizations are considered equal probable. For the purpose of our workflows, we'll consider them to be equal probable. Each one of them is going to be equally likely to be drawn, and therefore we can take them and build new distributions. That's very important. Okay, now in order to do this, in order to go from Monte Carlo simulation to making decisions, we need to fill in one final piece, and that is the transfer function. What is a transfer function? Not a big deal. This is not so hard. It's any operation applied to a set of realizations of random variables or random functions to assess the behavior over a spatial or temporal interval of interest. Now, the way I would refine that definition, it really is an operation that gets you from the random variables, their realizations, to a decision criteria. Because everything we do, I tell my students, if you don't impact the decision you have, you don't add value. You really have to impact the decision. I know. Sometimes we can explore and learn and so forth, but we really need to, at the end of the day, end of the year, impact the decision. Examples of transfer functions, just to kind of make this clear. A contaminant concentration calculated by reactive contaminant transport modeling. That would be the transfer function, to be able to go from a bunch of permeabilities and initial concentrations to what happens over time to figure out, how far did the plume go? Was there some type of bioattenuation or something in contaminant transport? Or dilution, if you're working in mining. That model by which you go from how you delineate it or engage material, the waste material, waste rock, and how you may have had error in that, or what was the heterogeneity in that, versus the selective mining units and your plan for extracting the rock. Put that all together into a model and you get a model of ore dilution. That would be a transfer function. And if we're talking about energy, we're talking about pore volume is very important to us, and connected pore volume, oil in place, and then recoverable oil in place, flow rate at a forecasted proposed well, pre-drill. All of those are important calculations based on transfer functions that are either volumetric or full physics-based flow simulation. Okay, now let's put that together. We have distributions of uncertainty, our random variables, for all of our inputs that go into our transfer function, x1, x2, x3, and we have an output from the transfer function, and the result is we want to get the uncertainty model in the output. Okay, so now what's very interesting here is that, let me just put some words around this to make sure this is perfectly clear. This transfer function could be oil in place, in which case the inputs in this function would be things like average porosity, thickness of the reservoir, saturation of oil, and so forth, and areal extent. And we could put it into a function, a simple volumetric calculation. And every time we do a Monte Carlo simulation, we get a realization, 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 put it through the function. We would get a realization of the output. And we could do that enough times and we get the actual distribution of uncertainty in the output, the decision criteria. This is the overall Monte Carlo simulation workflow. Monte Carlo simulation is the building block for the Monte Carlo simulation workflow that we're talking about here. Again, it's a very practical approach. It's a nice experimental approach. Some of you are probably looking at this and thinking, why? Why do we want to do this? Why don't we use just an analytical expression? Why would we want to simulate the problem? Why not just go at it directly? And I'm there with you. I'm going to agree with you. If you're interested in going at it directly, get it by an analytical solution, you can do that. Let's take problem number 1. The reservoir volumetric uncertainty is Gaussian distributed, mean of 100 million meters cubed, standard deviation of 15 million meters cubed. Okay, so we have a specific reservoir volume. We want to go ahead and calculate the uncertainty in the recoverable resource, assuming a certain recovery factor, and of course, accounting for conversion from meters cubed to barrels. Okay, not a big deal. So we've got a constant being applied to the random variable, which is that initial volume in place, that distribution right here, that's Gaussian. Now, if you use statistical expectation, you can show that if I apply a constant to a random variable, that in all generality, I can calculate its expectation as simply being the constant times the expectation of the original variable. So I'm just scaling the mean. And I can see that the variance, the standard deviation, can be calculated just like this. If we work with variance, we have to actually square the constant term. So we can go ahead and apply this constant, and we'll know that the new distribution will be Gaussian distributed with the mean shown right here, with the, the standard deviation shown right here and the mean shown right here. So we can work this out analytically. But this was a very simple problem. I hope you could all see that it was a random variable times a constant. Let's take problem number 2. Problem number 2 is reservoir is comprised of 2 units with thickness distributions that are known. The uncertainty distributions are known to us. Unit 1 has a thickness distribution. Its uncertainty is Gaussian distributed, normal score, with a 10-meter average and a 2-meter standard deviation. 13-meter average, 1-meter standard deviation for unit 2. Now the question is, what's the uncertainty in the total thickness of the reservoir? What are we dealing with here? X1, thickness of unit 1. X2, thickness of unit 2. And our transfer function is just the addition of the 2 units to get the total thickness of the reservoir. So what we need to do is we need to take this distribution plus this distribution to get a new distribution. Once again, we can appeal to statistical expectation, and we can see that the expected value, the mean, is simply going to be the addition of the 2 expectations, the averages. And the variance right here, we can see that there's additivity of variance as long as there's no correlation, no covariance between the 2 thicknesses, the random variables, and then that goes to 0, and we can simply add them together, and we can go ahead and get this final distribution right here. Central limit theorem, we know that it's going to still be Gaussian. We're in good shape here. Okay, so this is problem 2. We did it analytically. Where did the wheels fall off the wagon? Let's just up the complexity just a little bit. Calculate the oil in place given an average thickness that's uniformly distributed. The uncertainty distribution is a maximum entropy, what we'd call maximum entropy distribution. It's somewhere between 8% to 15%, and we have no clue in between there. It's not Gaussian, it's uniform. Thickness is log normally distributed with a mu and a sigma value. The parameters of log normal distribution. Area and saturation oil are constants. Now what we've done is we said that we don't get production if the average porosity is less than 9%. We have some type of cutoff. I know that's high. I know that's pretty high, but we'll call it non-net and we'll remove it. I hope you can see that that makes everything very complicated. In addition, we say there's a correlation between the thickness and the porosity. Where things are thicker, we have better porosity. Where things thin, it's a lower energy deposition, so it's a lower porosity. That's possible geologically. Okay, so we go ahead and we put all of that together. We cannot calculate the resulting analytical distribution. We can't do it analytically. It's just too complicated. This is a problem we could not solve using just analytical knowledge about statistics and how to combine parametric distributions. Problem 4 is where we can see the world is just a very complicated place. Solitaire. The probability of winning. You take a large combinatorial of possible outcomes with each hand and the cards on the table. You see the initial setting, what's in your hand, what's on the table, what's the order of the stack that you can draw from. Card ordering matters a lot. You have correlations and constraints imposed because of the fact that you don't have replacement. You have cards in the stack, they're not in your hand. There's going to be correlations. And you've got strategy and discrete choices the whole way through. This is the reason for Monte Carlo assimilation. These types of games of chance, there's no way we could work out the analytical solutions to figure out the probability of success or winning the game given a certain strategy. We can't do this analytically, and this is what drove us, the original developments of Monte Carlo assimilation is around how do we figure out these very complicated problems. So I hope you can see that the world is full of these types of complicated problems. I would say many of our settings are that level of complexity. Okay, I have a couple of more examples, but I want to go into demonstrations and show you some Monte Carlo. The comment I'd make is that in the notes here, I do show an example. You have access to them if you get access to the learning management system. They have worked out examples in Excel where you do random sampling from distributions, you add them together, you check the resulting output. And so you can see the impact of Monte Carlo assimilation and make these assessments. Let me go ahead. What I want to do right now is I want to shift gears and show some Python, because it'd really be a shame if I just spent the whole time talking. In a way, I kind of might be having too much fun talking about this topic, but I think it'd be kind of cool to show a nice example. All right. Now let me ask, by show of hands, are you able to read this font? Is everybody able to see this? This is okay? Thank you, James Chong. Thank you, everybody, for interacting. Mohammed, I do appreciate it. Very helpful to me. Okay, so these are the types of workflows I like to develop. I put some documentation. If people here have never worked with Jupyter notebooks, very, very powerful. You can build a workflow that has multiple blocks. Here's the first block. It's all marked down. It's documentation. Here's a work block that's code. Here's another documentation block. You see, you can build beautifully documented workflows. You can host things online. You can, when we teach real courses, actual courses within companies, we have everything hosted online. Everybody logs in. They can follow along. They don't have to do any installations. Okay. Now, and Avi, could you go ahead and help with any of these questions that are more about access to resources and stuff? I do appreciate the question. If you double click, you can actually see what I did to make that workbook. It's Markdown. It's anybody worked with LaTeX, it's a watered down form of LaTeX. You can make cool equations. You can make hyperlinks. You can make all kinds of great enumeration and formatting. You hit run and you get to see exactly what it looks like when it's all cleaned up and built. Okay, what we'll do here is we'll import, I wrote a package for spatial data analytics geostatistics. I wasn't finding what I needed. It's called GeoStatPy. We'll go ahead and import that. I recommend it. It does a great job of two-dimensional geostatistics. I use it in my teaching. There's more. If somebody wants to contribute, hey, develop code, co-authorship, you just need to jump in and you'll be recognized as a co-author. Let's go ahead and import NumPy. In our training, we teach about NumPy. We spend an entire half a morning talking about NumPy and pandas and matplotlib and scipy and so forth. I'm just going to import those packages because we're just doing a quick demonstration. I'll set a working directory so I can go ahead and load and save files to my hard drive. If I'm not working in the cloud, I like to do that. If I was, I could also use things like intake and manage the feature engineering or the data engineering up front and simplify my job. We'll go ahead and set up some distributions. We're going to demonstrate Monte Carlo simulation, a simple workflow for oil in place uncertainty in Python. And I'll show you just how easy it is to do. We'll set our distributions up. Gaussian for the average porosity, A pore. Volume of the reservoir, log normal. The oil saturation is going to be uniform. And we have a number of realizations, 1,000. So I'll set that. We'll go ahead and set some limits on the distributions we're going to create so we have nice plots that are all similar to each other. This is it right here. Here's Monte Carlo simulation. No correlations between any of the random variables. We're just simulating them separately. In NumPy, they have a random module. In that, they have a function called normal. You can set the mean and the standard deviation and create L or random draws from that parametric distribution, and that gets assigned to A pore. That's going to now be our random, our realizations, 1,000 of them. Okay, random realizations from the distribution. We'll do the same for volume from log normal, and we'll do uniform distribution right there. We run that. You know the old adage, no news is good news? Well, we didn't get any errors. Everything looks pretty good. What I always like to do when I run workflows in Python like this, in case you are new at this, I always like to take a look at what I created, check every step. We can go ahead and see that these in fact are random values drawn from that distribution. You could always do you could look at the statistics. You could also do things like look at the shape. And that's always a good thing to do. Make sure that what came out is in fact, it is a ND array from NumPy with 1,000 elements, one dimensional. And the final thing I like to do all the time is I like to do a little check and see, did I make what I think I just made? It's a NumPy ND array with 1,000 elements, one dimensional. So we can get rid of that. I always like to check every line as I go along when I do some coding. Let's go ahead and look at what we created. We just made 1,000 Monte Carlo simulations from the average porosity, parametric distribution, from the average volume distribution, and from the saturation, oil saturation right there. So those are the inputs for our oil in place calculation, and then we can go ahead and apply it. Now, what's really cool is we can use a broadcast method. If you find yourself in Python making loops, stop. Most of the time, you don't have to use loops if you're working with arrays. You can broadcast. This calculation right here is calculating oil in place, taking the very first element of the average porosity, first element of this, first element this, times our scalar in order to get into barrels. And we can go ahead, then it will do it for the second element all the way through 1,000. Then it's creating a histogram. This methodology in NumPy is very efficient. If you put a loop in and you loop over it manually 1,000 times, it's very inefficient. It'll slow everything down. We go ahead and run that, and we now get our Monte Carlo simulated distribution of oil in place, 1,000 right there. We can go ahead and check the results to make sure we're getting what we expect. We're checking the broadcast method versus we just do it by hand. In case you wonder, hey, does this really do what I think it does? Take the first element of each one of those ND arrays and calculate them by hand. And if you check, you'll see you get back what you expect. Okay, now let's go ahead and check and see what happens if you use a different big L, number of realizations. Well, if we do that, we can take a look at the result. We have only 100 realizations in each time. And if you look, what's happening here is we have different distributions. That's what it comes down to. You want enough realizations so that you converge on the truth. When people ask me how big of an L should you use for Monte Carlo simulation or for Bootstrap, my answer is enough. Enough so you can resolve with accuracy any desired statistical summaries and the distribution. Now I show an example. If you want to do non-parametric Monte Carlo simulation, drawing from a random set of values instead of from a parametric distribution, look at that. Isn't it beautiful? NumPy random module has a choice function. You give it a list of numbers and it will draw from it with replacement L times. We're going to use that for Bootstrap. That's a bit of a spoiler right there. Hey, Avi, thanks a lot for all you're doing. I can see you're helping people in the background. Thank you very much for that. It's really helpful. Okay. You know, I really do, Pyrcz, I don't know how to pronounce your name. I do apologize, but that is a very good question. I have a very kind of just heuristic approach to L. I say enough. It's usually a cheap calculation. I like to do quite a few, like 1,000 or more. At the same time, there are a couple of things we can do. The first thing we can do is we can think about what's the statistic we're trying to calculate. We can actually start to work out confidence intervals, and you'll see that not all statistics have the same width of confidence intervals. You'll need more to try to assess the tails than to assess the near the mode. The other thing, I agree with you, more complicated problems, you typically need more realizations. It becomes a combinatorial sampling problem. Okay, how are you sampling that high dimensional space adequately and given all of its constraints? So I think these are all really good points. Now, if you do want a mathematical approach to get to L, in my book with Deutsch on geostatistical reservoir modeling, we do propose a methodology to work out the L. And there have been other people who worked on that too. So I want to acknowledge there are statistical approaches. I do like the approaches just saying enough, like a lot. Okay, Bootstrap. Let's talk about the Bootstrap. Okay, statistical resampling procedure to calculate uncertainty in a calculated statistic from the sample data itself. You know the old English saying, pulling yourself up from your bootstraps? That's why we call it Bootstrap. It seems like it's not possible using the sample data to get uncertainty in the sample data. You see that? It seems almost circular. Let me reassure you, it does work. It uses repeated samples n times Monte Carlo simulations from the data set, from the CDF. Or basically another way to say it is you could take all your values, put them in a hat, draw a value out, record it, put it back with replacement. That's what I do with my students in class. I get my big cowboy hat. We do some type of a bootstrap simulation from green and red balls or something like that. You're going to build the entire distribution for uncertainty for any statistic you want to work with. Let me demonstrate it to you, and then we'll show it to you in code. A nice interactive example. I have 10 sample data. Make it something meaningful. It could be you had 10 wells and you have average porosity, permeability, something like that from each one of the wells. That's your histogram, 10 samples. You build the CDF, it's representative. You've done all debiasing, whatever else you had to do. You do 10 Monte Carlo simulations from the CDF. It's the same thing as 10 times drawing a well with replacement, put it back in hat. If you do that, you will get a new realization of the entire distribution, the histogram. What you can do then is calculate the statistic of interest, the average in this case. That is a realization of the statistic. You record it. Now, what do? You do it again. I do another 10 Monte Carlo simulations, the number of data, Monte Carlo simulations. That's a bootstrap realization of the distribution. You calculate the statistic of interest again, you get another realization. Repeat, repeat, repeat. You do it L times, where L is enough. If you do that, you will get the entire uncertainty distribution in that statistic of interest. You see that? This is super, super powerful. I teach quite a few students. My machine learning course, I had like almost 80 students, 75 students. I got them to do a little uncertainty modeling as part of their data preparation stuff up front before the machine learning. We did the bootstrap for uncertainty in the Dijkstra-Parsons. So remember, you could apply this to any statistic of interest. The 10th percentile, the 90th percentile, the P50, the Dijkstra-Parsons, the Lorenz coefficient, the correlation coefficient. Anything you want to, you can use the bootstrap, any statistic. And in fact, we use it in machine learning on models, random forest, tree bagging. Those are actually bootstrapping applied to make multiple ensemble learners or multiple models. I go into machine learning. Sorry, let me stay here. Let me make a couple of comments around the bootstrap. I showed it to you in a graphic. Developed Ephron back in 1982. Great paper to read. Statistical resampling procedure to calculate uncertainty in a statistic from the data itself. And if you don't believe it, do the uncertainty in the mean, compare it to this calculation right here. This is the analytical expression known as standard error in the mean. It is the variance of the mean given the original sample variance divided by number of samples. It will match that. The variance of your bootstraps realizations, your new distribution will match this. Extremely powerful, could get uncertainty in any statistic. This is, you can advance it, you can move it forward, you can put strategy in it, you can go into like game theory, you can make it much more complicated. Now, if you are interested, let me just make a couple of comments about it. It's one of the most powerful statistical developments from the 1900s, I would say. Assumes the sample set is representative. There's no bias in the sample data. Unbiased covers the full range, nothing missing, no imputation problem. Assumes all samples are independent. Now, if you can't, which is often the case in spatial context, then you have to use Spatial Bootstrap, okay? And I have demonstrations, we talk about Spatial Bootstrap too. You could do Bootstrap in Excel. If you go to my GitHub repository, to my Excel numerical demonstrations, I have bootstrap_demo. You can actually take any list of numbers and get multiple realizations of that distribution. And you can get all these statistics and look at the uncertainties in those statistics from Bootstrap. So if you wanted to, I'm not teaching from Excel here, but if you wanted to, you could just do it in Excel. Very easy to do. You just use the random values in Excel and some other database operations, you can make it happen. Let's go ahead and let me show you an example of Bootstrap done in, let me see, Bootstrap done with an interactive example. Bootstrap, interactive Bootstrap right here. Can everybody see this font? Is this font okay? Do you want me to zoom in or out? Everybody, John, thank you, Matt, Jeff, Daniel, thank you very much, guys. Sarah, I do appreciate, guys. Hey, howdy, everyone. Yeah, good to see everybody. Okay, so let's go ahead. I do appreciate that. Let's go ahead and we'll walk through this. This is Bootstrap. What is the example? The example here, I like to give lots of explanation up front, but what we're going to do is we're going to use Matplotlib and IPy widgets to make an interactive display. Okay, so we have this on the learning management system too. You can go ahead, I won't walk through the code, not for this one, because I don't have time to really teach this, but here it is. I have a hat. The hat has a number of red balls, a number of green balls, and I have L realizations bootstrap. In other words, I have a cowboy hat with 2 red balls, 3 green balls, and I have students, and I do this in my class, and they're sitting there. One student's holding the hat, one student's grabbing balls out, and one person's recording it on the board, and they're counting, and we have multiple realizations. Realization number 1, you could get 4 red balls and 1 green ball. Can everybody see that that could just happen? That's not unlikely. You could have 2 red, 3 green balls, because we did 5 random draws with replacements. The only thing I do know is that this plus this will be equal to 5. And right here, realization number 3. Now you could increase the number of realizations, and what this workflow will do is show you kind of different draws you could get. And you could go all the way up to many, many realizations, and some pretty interesting things can happen, like almost only 1 red ball and 4 green balls, that could happen, and vice versa, and so forth. Now, how do we get uncertainty? Well, the uncertainty here would be the uncertainty in the proportion of green and red balls, because every time we did this, we got 80% green balls, 20% red balls, and so forth. We could calculate those distributions. And that's what we're going to do right here. So we'll run this one right here, and we'll get interactivity. Let me zoom out a little bit, where what I can do is let me just change the number of realizations, because what was happening, I had so few realizations, the plot was not working very well. I have about 227 realizations, 2 red balls, 3 green balls. And this is the histogram of the number of balls, red. This is the histogram number of balls, green. And this right here is the proportion of red balls. Now, we could go ahead and increase the number of balls. I hope if I increase this to a relatively large number, you can see, and if I do enough draws, I hope you can see now that we're in a situation where this box and whisker plot showing us the interquartile range, the mean, the outliers, and so forth, we can now see the uncertainty model in the proportion of green balls, proportion of red balls, just by doing Bootstrap. Now, of course, I can change this dramatically. So the number of red balls in the hat is significantly lower than the number of green balls, and you can immediately observe the impact on the result here. Okay, now, what do you think? Let me ask you a question. What should happen to the uncertainty as we increase the number of red balls? What do you think will happen to uncertainty? Will it go up or will it go down? Anybody? If I just increase the number of red balls, the uncertainty in the red proportion, what will happen if I increase the number of red balls? In other words, the number of samples that are red. Well, let's go ahead and try it out. We can go ahead and shift this to a very high number. Higher and higher and higher. And if you look really, really carefully, what you'll see is that what's actually happening is that the uncertainty overall is shrinking in the proportion of red, and it's shifting higher. In fact, if I was to, you see how much that shifted? The uncertainty is being reduced greatly. Now, if I increase the green balls too, that uncertainty will continue to fall. In other words, the uncertainty in the proportion of red or green or any outcome will go down as we have more samples available to us. Okay? And so in general, even if I kept the same proportion, even if I took this and left it as, let's leave it as 4 and 6 right here. So we have 40% red balls, 60% green balls. Look at the uncertainty now. Now you have to apologize. There's a lot in law of large numbers. Thank you very much, Sandra. There you go. Yeah, exactly. You see how wide this uncertainty is in the proportions? Now, if I go ahead and I retain the same fraction, but I say, okay, instead we'll say 40 and 60. What we can see here is that we retain the same expectation for the proportion of 40% and 60%. But what we're going to see overall is the uncertainty in that is going to shrink. And Sandra was hitting it right there. We know that in general, this is showing us the significance of the result, the law of large numbers, and protecting us from a false belief in the law of small numbers. We're going to realize that the outcomes of individual realizations, if there's very few number of balls, can be dramatically different. Like we saw before, it can jump around a lot if we only have like 5 balls involved in the draw. Okay, so this was an interactive display to show us some of this Bootstrap. I think it's really good to show a more comprehensive, more tangible, or more practical workflow for Bootstrap. This is a workflow right here where we demonstrate the calculation of uncertainty in oil in place given a Bootstrap approach in Python. Let me go ahead and run through this and I'll give a couple of comments around it. We can do all of this using very standard Python packages. This is not complicated at all. We can set the working directory. We'll go ahead and load up a data set. We have a bunch of these realistic data sets to work with. We'll work with 260 samples from the data set, and we can do a little bit of a preview. In regular courses, we'll explain much more about how to work with data frames and tabular data with pandas and so forth. Here, I'm just showing you that we have a nice data set with XY location, facies, porosity, and permeability. We can also do some statistical summarization. We can look at the statistics, the mean, the standard deviation, the min, the max, the quartiles of all of our features very nicely. We can go ahead and visualize our data too. Let me show you some nice visualizations. The Geostats Py package has some nice wrappers for Matplotlib with one line of code. You get a nice location map standard that you'd see within Geostatistical Library. You could also work just directly with Matplotlib and produce nice flexible plots. Here's an example. I'm not going to show you declustering today, but to debias the data, and I hope we can see this, the high porosity colors are bright, kind of the light yellows, the blues, the dark blues are the low porosity values. I hope you can see that we have a biased sampling situation. We'll apply a cell-based declustering method to debias the data. We don't have enough time to talk about that today, but we can go ahead and decluster the porosity. Now, what's really cool is I can apply that one NumPy approach. NumPy package random is the module. We have choices as the function. We feed it a one-dimensional ND array with all of our porosity values. We give it the declustering weights so we don't have a bias in our outcome. And then we can go ahead and calculate K equal to the number of data random draws from the distribution. So this is giving us a single bootstrap realization of the distribution. The original declustered distribution shown here, porosity. Here's one bootstrap realization. Here's another bootstrap realization. Isn't that cool? So with that one line of code, we can create a bootstrap realization, and guess what? We can loop, and make multiple bootstrap realizations, not a problem. So what we do here is we loop over that command, and we can now make multiple bootstrap realizations, and we calculate the uncertainty in the porosity average, the uncertainty in the standard deviation. So we now have this as a bootstrap distribution uncertainty. We get the summary statistics. We can talk about the P10, the P90, or reversed if your company uses the reverse notation for the percentiles. And you can do that for standard deviation or any other statistic of interest. Very simple to do Bootstrap in Python. Now I want to show one last thing about Bootstrap, and I think this is really cool. Actually, by show of hands, who's working with confidence intervals or hypothesis testing as part of their job? Something they kind of do frequently. Daniel, I see you. Jeff, I see you. Tim, Jennifer, Alan, James, very cool. Muslim, very, very cool, guys. Very cool. It's good to see we got people out there using standard statistics. I agree. I think it's very important to go back to fundamental statistics. Even if we're doing machine learning, I think it's very important. Remember that when you do confidence intervals or hypothesis testing, you can get the sampling distributions by Bootstrap. I demonstrate this for confidence intervals here, and you can do the same thing by hypothesis testing. Okay, so what have I done? You remember our example where we had interactive number of red balls, number of green balls, and I'm sorry, color of balls. It could be net and non-net. It could be a ore versus gangue material. It could be whatever, contaminated versus uncontaminated. Whatever you want, it could be any category, indicator, group classification. In this case, it's red and green balls for demonstration. Then what we have is we have the number of realizations we want to do Bootstrap for. And what this program does is it does the Bootstrap realizations. Okay, so we get the Bootstrap realizations for the proportions of red and green balls. Then what I do is I take the analytical expression. The people who mentioned they do confidence intervals will know about this. The student T distribution, or if you have a large enough set of samples, it converges to Gaussian. This distribution right here is the analytical expression. So if anybody is concerned about the use of Bootstrap, you can compare it when possible with analytical expressions like this case. And if anybody is trying to do confidence intervals and hypothesis testing, and you want a simple general approach that's very intuitive, you can use Bootstrap approaches in order to get to that, which is very powerful. In other words, Bootstrap gives you the uncertainty in the proportion. So if you want to talk about confidence intervals, you need that uncertainty distribution to assign these the upper and lower bounds given a significance level, alpha level. You can go ahead and just calculate that through Bootstrap. And that's what I've demonstrated right here. The bar chart is Bootstrap. The lines are, the curve are the analytical expression. So you can do both ways. Very, very powerful indeed. I've seen statistics courses where they teach everything from Monte Carlo assimilation and Bootstrap rather than the analytical forms, which can be very intuitive. Okay, let's go back and finish up with a couple of concepts, ideas. I've shown a bunch of different workflows. In our regular courses, we have discussions more. Everybody's off mic and we're talking. Often we have smaller groups, which is really nice too. We spend a lot of time together. Bootstrap, I want to give you a challenge to do in your own time. Hey, let me know how it goes. Go ahead and work out the uncertainty in the mean porosity for unit B given wells all with average porosities measured over unit B. Go ahead and give yourself a nice example, work that out. I have example data sets that you can use. There's a 12 well example I have. I don't have the link here, but I can put that out and share it. Go ahead and attempt to do this. Get the bootstrap uncertainty in the average porosity given a limited number of wells. Try it out, try it in code. It's really fun. What did we cover today? Uncertainty sources. There's many sources of uncertainty. Most of our model inputs are uncertain. We need to explore. I say we need to be uncertainty sleuths. And the bootstrap approach is a very good way within its assumptions, like IID, independent identically distributed, to be able to get at those uncertainty distributions. Monte Carlo assimilation, there's no analytical solution for many of our uncertainty problems to propagate, to integrate uncertainty all the way through the decision criteria, like the contaminant level, like the oil in place recovered, and so forth. Monte Carlo assimilation provides a very practical, intuitive approach to be able to integrate that under its assumptions. Bootstrap assess uncertainty in a sample statistic or model from the sample itself. And we can use Bootstrap to build the input distributions for an overall Monte Carlo simulation workflow, which is very, very powerful. I think that's a very useful thing to do for overall uncertainty management. Okay, thank you very much for everyone for your attention and for joining in today. Avi, did you have any parting things to say?
No, that was it, Michael. Thank you for your time. Yeah, for anybody interested in we have some more webinars coming up, so stay tuned for that. Yeah, hopefully we can all measure uncertainty now. So.
And sorry, Avi, my speaker turned off. Are you talking?
Yeah, no, thank you for your time. I think this is really good. I hope we can all measure uncertainty now. Bootstrap's great. Stay tuned for more webinars. I know Michael and John will have some more webinars coming up. So.
Hey, thanks a lot, Avi. Appreciate that. I'll tell you what, everybody, I'd rather be in person. So let's simulate the in-person environment. In other words, I'll hang out here for a couple of minutes if there's any questions. I do apologize. At 2 p.m., I'm going to teach at a company, and so I really do need to run right at 2. But if there's any quick questions, I'm happy to discuss. Okay, and James had a question. Does bootstrap distribution represent the distribution of the mean uncertainty as a whole, or is it the overall distribution? And that's a very good question. Bootstrap gives you realizations of the data. Okay, so realizations of the data distribution. Then you can go ahead and get realizations of any statistic of interest. And the result is you get the entire distribution sampled of that statistic of interest. Now in machine learning, you actually get models. You get multiple models and samples of that. But for us, it's just realizations of the statistic. In other words, it does give you the entire distribution. You're sampling it. And that's why we say L needs to be large enough so that you have enough samples that you can actually resolve that distribution. If I only have 10, I can't really talk about resolving the P10 and the P90 if I only have 10 samples. You need enough to be able to see it. So, oh, sorry, just checking this out. Now there's a question here about MCMC. We do cover in our courses, we talk about Monte Carlo Markov chains approaches for sampling. We specifically do it in the context of trying to deal with the use of Bayesian approaches. Bayesian approaches in machine learning like linear regression, Bayesian linear regression, where you have a prior and you're sampling to the posterior of all of the model parameters. And in that case, it turns out that it's a very large problem. We can't just solve it directly. We have to sample it. We need to get an equilibrium chain with MCMC to be able to actually sample at it. It'd be hard to get into all the details of MCMC right here. Any other questions or comments? Hey, thank you very much. I do appreciate the people who expressed appreciation. Jennifer, Tim, Kuam, Jeff, thank you very much, everybody, for jumping in. I do appreciate that. Reza, you had a question, 2 questions. How do you know what is the type of curve to select for each parameter? You really get at an important point right here. And that is, what should be the distribution of uncertainty? What should be its shape, its form? And in my examples for Monte Carlo simulation in Python, I assume some parametric forms. Now, the good thing is this: if we're using Bootstrap to get the uncertainty in a specific feature like average oil in place, the cool thing is that we're actually using Bootstrap to get individual samples. And so we sample the entire distribution, as I just said. As a result, the actual distribution empirically comes back to you. You get to actually see it as a result of the Bootstrap. Okay. So in general, you'll find that that can come back. Now, at the same time, I want to be very careful because I'm talking about as if it's a done deal. Bootstrap has limitations like IID. Many of our problems have spatial relationships, non-stationarities that violate independent, identically distributed assumptions. And so we got to be a little bit careful around that. The impact of that is often more complicated distribution shapes. We often deal with things that are kind of log normal, positively skewed. I feel that has a lot to do with the fact that we have non-stationarity, areas of kind of high, limited areas high, and then areas of low. That can feed into and result in those distribution shapes. We can also have multimodal distributions. Okay. I do have to run to go meet with a company right now. I do appreciate everyone joining in today. Avi, thanks a lot for helping.
Thanks, Michael. Appreciate it. Talk soon.
Hey, we'll see you. Bye.
Bye.
Thanks, everyone. Bye.